Okay, so let's go ahead and get started with class today. Today we are talking about kind of a very unique feature of 4-bars, which is cognates, which is basically saying that any 4-bar has two other cognates that traverse the exact same path as it does. And so if you synthesize one mechanism that traverses a path, there's two others that traverse the exact same path, and there's some graphical methods to figure out where that is. So first of all, I'll talk about the construction of this, talk about some applications to both 4-bars and geared 5-bars and 6-bars, how we can make a parallelogram or a parallel motion mechanism. And then we'll talk about some extensions of this to sliders and some other situations that are a little tricky to deal with. Okay, so a quick introduction to cognates. So you often hear this referred to as either the Roberts theorem or the Chebyshev theorem or the Roberts-Chebyshev theorem, depending on where you are. So the French will talk about it as the Roberts theorem, the Russians will talk about it as the Chebyshev theorem, but really these are two guys who came up with just about the same thing from fairly different approaches around the same time. So Roberts came up with it in 1875, Chebyshev in 1878. They were both mathematicians, members of the Royal Society, so fairly well regarded. And the idea of this cognates theory is that, again, three different 4-bar linkages will trace identical coupler curves. So here you can see in the left side, I've got a 4-bar mechanism, and I'm traversing this coupler curve labeled with the coupler point M, or the precision point M. And then I've got another one right here that's traversing the exact same coupler curve, and I've got a third one right here. And I can actually put all of them together if I wanted to and create an over-constrained mechanism, but this would traverse the exact same coupler curve. So all three of these traverse the same coupler curve. Very interesting from a mathematical and kind of academic perspective, but also is very useful in a couple of different ways that we'll talk about. So before we get into talking about how these are created or how we use these, let's talk about how we construct them. So I've drawn some arbitrary 4-bar right here, and we're going to use what's called the Roberts construction. We'll then go to the Cayley construction a little bit later, again, this one I think is a little bit easier to use and a little more intuitive. So the first step here is that I'm going to add on a pair of parallel links from what I'm considering to be my input link over here, and then I've got a parallel one to that that's connected to the precision point, and then I've got the piece of the coupler between the precision point and that input link, and I'm drawing a parallel link to that over here. So I have a parallelogram that I've constructed here on the left. And I do the same thing on the right side of my mechanism, and again, now I have a parallelogram over here. So this length right here, the coupler is the same as this length of the output length is the same as that length. The next thing I do is I use similar triangles. So you see that I have my coupler with different dashes inside of the pieces of the triangle to denote different angles. So you can kind of track these. So what I'm going to do is create a similar triangle with that side that I just constructed, that parallelogram construction. And so I'm basically going to be just shifting this up so that this angle here that has the triple on it will then move up to the coupler point. I can do the exact same thing on the other side of my mechanism so that this point over here that's connected to the input link will now move up to the coupler point. And you can see these two, what will become the new couplers of these cognates of the initial mechanism. So I've got the initial black one, and now I form this blue and red cognate coupler. And again, I've just done this through similar triangles and through parallelogram constructions. The very last thing is to add two more links to make a parallelogram here. So I've got this side of this coupler and this side of the red coupler, and then I create a parallelogram with all of these. And this point right over here becomes my new ground pivot. So I started off with only two ground pivots, and now I've located this third ground pivot. And so all three of these mechanisms, I think I've got this animated. Yeah, so all three of these mechanisms will share the exact same path of this point. And if you start counting these up, I now have a 10-bar linkage, starting off with my initial 4-bar, adding in 3 more for this red mechanism, 3 more for this guy right here. And again, ground counts as 1 all the time. So we've got a 10-bar mechanism. If we do a Grubler's equation on this, we've got a -1 degrees of freedom, so we're over-constrained. But due to the fact that we have this perfect cognate construction, and if all these links end up being the correct lengths and we have all of our pivots at the right points, this will be mobile, even though Grashof tells us it won't. And so I can take all three of these guys and I can separate them out. So all three of these are sharing the same path. Recognize that through the coupler construction, or through the parallelogram construction, these do not share the same coupler rotation. So what do I mean by that? Well, notice that link 2 right here, what used to be my input link, because I've got a parallelogram construction, link 9 right here will share the same rotation. So omega 2 is equal to omega 9. And then again, due to the parallelogram construction, I can jump across here and say omega 7 is also equal to omega 9, which is equal to omega 2. I've got a few other relationships like that where I've got my output link, link 4, being the same as this red coupler, link 6. And then I jump across this parallelogram, and that's the same as omega 8. And then I can take the initial coupler, omega 3 right here, and I can say that the angular velocity of link 5 and the angular velocity of link 10 are the same as that. And that's, again, just due to this parallelogram construction within here. So I can take this and I can spread these three guys out. So now I have three unique mechanisms, a black one, a blue one, and a red one. And all of these will traverse the exact same path in space. So I've got a whole different bunch of ways that I could use this. Anything from saying, well, I created one of them and I didn't like a ground pivot, so let me create this cognate and figure out where that ground pivot is, and maybe it'll be better. All the way to some more complex ways of using this in 6 bars. So before we get to the uses, a couple other notes to make on this. First is looking at Grashof criterion for these. So if the original mechanism, or of any of the cognates I should say, but let's say the original mechanism is a triple rocker, a non-Grashof triple rocker, then its 2 cognates are also triple rockers. So it's a forcing function of the fact that, S plus L being less than or equal to P plus Q, the way we've set this up with a parallelogram construction, we're always going to have non-Grashof mechanism form non-Grashof mechanism cognates. Alternatively, if one of my cognates is a crank-crank, and remember that a crank-crank, we've got that S plus L less than P plus Q, so we've got the Grashof condition satisfied, plus the shortest link is my ground for the crank-crank. So if one of them is a crank-crank, then they all are crank-crank mechanisms. So kind of an interesting piece there. And then the other option is that if 2 of the cognates are crank rockers or rocker cranks, then the other one is a Grashof rocker. So you do get some sharing through the Grashof criterion of just through the constructions and the equal lengths created here. Now I'm going to talk about just one other way to construct this as well, because this is useful for some special case mechanisms where the Roberts construction doesn't apply. So this is what we call the Cayley construction. So I'm taking an initial 4-bar mechanism here, and I unpin the 2 ground pivots. And so you can imagine I take those 2 ground pivots and I rotate them to a point where I now have a collinear input link, coupler link, and output link. And here I'm referring to the coupler as the 2 moving pivots. So all 3 of those pivots, the 2 grounds and the 2 moving pivots, are all collinear. So I've unpinned this. And then I take this unpinned mechanism, so that's links 2, 3, and 4. And first of all, I take my coupler and I create a similar triangle that goes from ground pivot on the A side, ground pivot to the B side. So that's the base of that's the moving pivot to moving pivot of my coupler. And I extend that out with a similar triangle out to this new moving pivot, new ground pivot, which we call OC or C naught, however you want to refer to it. So this is a similar triangle right here to the coupler itself. The next thing I do in this is similar parallelogram construction, where link 5 right here is parallel to this side of my coupler of link 3, and link 10 is parallel to this side. And then just due to the fact that I've straightened all this out and made it a straight line, I've got a straight line from what I'm calling A2 to the precision point to A3. So all those are a straight line. And then I create two couplers, 2 new couplers, which are similar triangles to the original coupler. So I just take the original coupler and I move it up here, and I've already got one side of it defined, so that defines the scale of this. And then the angles stay the same as coupler 3 or link 3 as I go to link 9 and I scale it. And then I do the same thing with link 6, where I've already defined this P to A3 point right here, and I scale this up just a little bit bigger, but again, similar triangle. And doing that then locates B3 and B2. I've already located that ground pivot OC in this case. And this similar, similar triangle construction has created this. The very last step that I do, and maybe I'll leave it on this page right here, is I take these two ground pivots, OB and OA, and I pull them back down to their original conditions or their original points. And in doing so, it moves the entire mechanism, if you will, pulling OC down to a new ground pivot. So OC is kind of floating in space right here, right now. Once I pull OA down and I pull OB down, you can imagine this guy's going to come down and locate somewhere right around where I've got my laser pointer right now. And then that is this constructed parallelogram mechanism. So we call this the Roberts diagram, but it's the Cayley construction of that. And again, I can take this now and break it apart. So the trick of this is that I have to pull these two ground pivots back to their initial condition from that collinear condition, and then that moves OC down. And then I can separate out the three different cognates of it. Any questions from those of you who are here? Thoughts? Okay, so two different ways of constructing this, one with the Roberts, one with the Cayley construction. And again, we'll talk about how some of them only apply to certain types of mechanisms. So let's get into applications. First one is looking at 4 bars and how we create some alternative solutions there. The second one we'll move into approximate or using a 4 bar to approximate a geared 5 bar, or vice versa. And then we'll talk about a parallel motion 6 bar, which gets us very complex or fairly complex motion while still being able to have a coupler that is parallel at all times. All right, so talking about a 4 bar mechanism, we've got two alternative solutions right here. And so, the real benefit is that if we synthesize an initial path generator and we don't like its ground pivots, what we can do is we can pick its cognate. So if I've synthesized this 2, 3, and 4, the black one, I could say, well, this ground pivot over here by 2 is fine, but this one over here just doesn't work for me. So I can grab its cognate of the blue mechanism over here, 8, 9, 10. Or vice versa, I could have 5, 6, 7 if this lower ground pivot of link 2 didn't work very well. So I can create alternative ground pivot solutions. The other thing that I can do is I can synthesize a path generator with prescribed timing. So in a path generator with prescribed timing, I'd be concerned about the movement of the coupler point here in space, this point on link 3, and the rotation of link 2. And I can take that information and I can create its cognate, and now the cognate will have that same path in space, but now the coupler rotation will be the same as what the input link timing rotation used to be. So due to the parallel construction, link 2 and link 9 have the same rotation. So if I synthesize it so that I get the rotation I want in link 2 with the point I want moving in space in link 3, I can create its cognate. Now I have a motion generator from a path generator. I can do the same thing in kind of a vice versa approach where I create a a motion generator, and then use that to create a path generator with prescribed timing. But again, recognize that these couplers do not have the same rotation angles, but I can use the fact that one of my input links will have the same rotation as one of the couplers. So this is another way to apply it. A little bit challenging, because the problem is with this cognate construction, you don't know where that ground pivot's, or when you synthesize the base 4 bar, you really don't know where that ground pivot's going to end up yet. So you could end up with a pretty poor solution and done a lot of work to get there. But this is the way that it has been used in the past. Now, a more interesting way that's a little bit more popular is that we can create a 4 bar, and then we can create that exact same motion with a geared 5 bar. So any 4 bar coupler curve, that coupler curve can be reproduced with a geared 5 bar. And this geared 5 bar will be one where we've got the same, basically got one-to-one gearing, so that input link and output link both rotate in the same direction at a one-to-one ratio. So let's talk about how to do this. So first of all, I'm going to create the same parallelogram construction on the left and the right side. So I'll create this blue and the red links. Once I've got this, now I can start to recognize that the rotation of my coupler is the same as the rotation of this new link pinned to ground on the left side, that blue link, and the link pinned to ground on the right side, the red link. So that information, I can say, well, if I force the rotation of the blue link pinned to ground, the red link pinned to ground, if I force those to be connected through some sort of a gearing or a belt or something like that, I can then create the exact same motion of this coupler point. So if I add up these two blue links plus these two red links, I've got a 5-bar mechanism. But if I set up a relationship between the rotation of this and the rotation of this through some gearing, now I have a geared 5-bar, which would have a single degree of freedom. So let's take a look at this. Okay, so here's how I would set it up with gearing. And again, I'm going to force the rotation of this one to be the same direction as the rotation of this, and so that's why I need an intermediate idler gear to change my rotation direction, so that I've got, in this case, I'd have a velocity going up and to the right here, and then I have a velocity going down and to the right here to create counterclockwise rotation of both of these links. So this would then be, this gear would be rigidly connected to this link, and this gear would be rigidly connected to this link. So that gear would then rotate with that link, forcing the rotation. So that's how I'm connecting those. I can also do this in a few different ways. So then this is the final solution to that geared 5-bar. Another option, you might say, well, you're doing, one-to-one velocity. Why stick that idler gear in there? So one alternative is that I can just create a belt drive, something like this, where I would create maybe a timing belt between the two of them, something like a cog belt or something like that, so I don't have slippage. But it just replaces the fact that before I had a gear, and gears are a little more expensive to create and get the center-to-center distance just right. Now I can just put a belt in there and get that same effect. And so now I have a belt-driven 5-bar mechanism. And again, now these sheaves right here, the belt, would be rigidly connected to these two links pinned to ground. All right, so I can do this with belts, I can do it with gears. How about any pure mechanical links? Thoughts? How could I do that? Well, what I'm going to suggest is that I can create a parallelogram linkage. So what I'll sketch is maybe something coming off like this, and these two are rigidly connected. And then I'll create this one, hopefully parallel, same length, and so that blue link and that link are rigidly connected. And then I will have these two moving pivots right here, and I will connect them with a link. And so I formed a parallelogram linkage. And what this parallelogram linkage is now doing is it's forcing the rotation of this blue link, which is coupled over here on the left, same rotation as this guy over here. So I've created the essence of a geared 5-bar, but now in a pure linkage, and not had the complexity of having to either buy gears and get the center-to-center distance right, or having a belt that wears out, or whatever else. So I can keep this in a pure linkage solution with a parallelogram driver, if you will. So this is really a function generator that's doing a one-to-one function generation of input to output. Yeah, question?
So is like that bottom link not count? How exactly are you getting a 5-bar?
So how am I getting a 5-bar? You're right that I have jumped up to now a 6-bar mechanism.
Same with when you had the idler gears at a 6 bars.
So the question was, if we had the idler gear, you're right that the idler gear counts as you would technically count it as an additional link, if you would, and so it would be a geared 6-bar. But because we think about it as just the main links of the mechanism as being, or we only think about the pinned links usually, and so a geared 5-bar, we normally don't count the gears. But from a purely correct standpoint, you're exactly right. You should count those, and you count the idler. And then in this case, you would again have ground as being 1, and maybe link 2, which is this entire link right here, link 3, 4, 5, and then 5 is this entire link here, and then link 6. Yeah, so you're exactly right. Good question. Anything else? Okay, so here we can use it in a geared 5-bar, and lets us approximate a 4-bar with that. And again, the usefulness kind of depends on the certain situation. You might say, well, isn't a 4-bar always simpler? There are situations where perhaps the geared 5-bar might fit in better with the rest of the mechanism, where you might already have other timing constraints, and for some reason the geared 5-bar might be a better fit. All right, so this is where this tool is used probably most often. This is in a parallel motion type of an application. And so let me first of all sketch in what would be the alternative to this. And the alternative is a pure parallelogram type of a linkage, just like I had sketched in the previous plot to drive that. And so I've got a 4-bar mechanism, and I can have a coupler point that comes up here to do something. This is my coupler. And my coupler is able to maintain parallel motion due to this parallelogram construction. The problem is that a 4-bar parallel motion only has circular motion. In other words, this point right here goes through a circle, this point right here goes through a circle of the same arc, and therefore our coupler point only goes through a pure circle as well. And so our motion is very constrained. We really can't create any kind of interesting motion. Our coupler is purely a circle, a coupler curve. So, normally we want the ability to use a little bit more interesting coupler curve with a 4-bar mechanism, and that's where this cognate construction comes in. So I can leverage the fact that I've got cognates that are creating points that have the same path in space to help me create a Watt-1 parallel motion machine. And so I'll kind of go through the steps of this. And before I do, let me first of all say that what you're going to synthesize here is you're going to synthesize a base 4-bar. And what this base 4-bar is going to do, so I'll synthesize 2, 3, 4. I'll be synthesizing this path moving through space. So this is what I would want the parallel motion of. So let's say you've got an example of maybe a wheelchair loading mechanism where somebody drives their wheelchair up onto a lift, and then that lift comes up into a bus or something like that. Well, in that case, you don't want to be dumping the person on their wheelchair, and so you want to keep that parallel motion. But you need fairly complex motion as well. So you would synthesize a path that's going to move through in space, that lift is going to move through in space. And that would be this point right here. So this would be a path generation problem. And then what I'm going to do from here is I'll say, through this cognate construction, I've recognized that link 2 and link 7 have the same angular velocity, and realize I've thrown away that extra cognate here that forced that, but this was part of the construction. So link 2 and link 7 have the same angular velocity or the same rotation as they move this point through its coupler curve. So I'm going to take that and I'm going to slide that ground pivot that was associated with link 7, I'm going to slide it down to be coincident with link 2. So that these two will share the same ground pivot, and then I'm going to rigidly connect links 2 and link 7 so that they rotate together, so it now becomes a ternary link. So I've got ground pivot, a pivot here, and a pivot here. And then I'm going to connect the two coupler points. So again, let me back up a little bit. Remember, I've got these two sharing the exact same point in space and saying they share the same path. They're cognates of each other. And link 2 and link 7 have the same angular velocity ratio, or rotate at the same angle. So as I bring this guy down, force 2 and 7 to become a ternary link, then this coupler curve right here is going to be the exact same as this coupler curve right here. So if I connect those two with a link, that link is going to have parallel motion. And it'll have parallel motion along the same path that this initial 4-bar had. So this then becomes the constructed mechanism. Now we still have an overconstrained mechanism here because we've got these two cognates and they happen to be linked together here, and I'm also forcing this to be a ternary. So I have an overconstrained mechanism here. So what we can do is we can throw away, and let me kind of do that again, I'm going to throw away this link 5 over here and then collapse this coupler down so that it only consists of going from this moving pivot to the moving pivot with the link that maintains parallel motion. So I'll collapse that down. Link 6, which used to be part of the coupler curve, part of this lower red coupler, has now collapsed down. And so this link that's labeled 8 right here ends up becoming our parallel motion link. And so now we're left with a 6-bar mechanism, ground being 1, 2, 3, 4, and then 5, 6. 5 being what's labeled 6 here, and then 6 being this parallel motion component. So kind of backing up, doing this quickly, say 2 and 7 share the same rotation. These two coupler points share the same path. So I bring those down and force 2 and 7 to be rotating together by turning them into a ternary, and then connect these two coupler points. And then that creates this mechanism right here, which is over-constrained at this moment. And then because it's over-constrained, I can throw away that additional constraint, forcing this into a Watt 1 6-bar mechanism. And so this link that's labeled 8 right here will have parallel motion. And that's where you put the person on their wheelchair or whatever else you want to have parallel motion of, and still maintain a fairly complex 6-degree coupler curve. And again, because I can synthesize this base 4-bar as a path generator, this can be pathed with prescribed timing, so I can have prescribed timing for my parallel motion generation. So pretty powerful tool here, and this to me is the reason to talk about cognates. Yeah, it's a very interesting thing that we can create these other mechanisms and perhaps do swap out of ground pivots, but the really cool thing is that we can create this parallel motion 6-bar mechanism, which is extremely powerful. So consider this if you have a problem that needs close to parallel motion in your project. Any questions before we move on from there? Are we good? Okay. So a couple of cognate extensions, and I'm going to cover these fairly quickly, but just want you to recognize that these exist. So first of all, when we're looking at slider mechanisms, instead of having 2 cognates, every slider crank mechanism has 1 slider crank cognate. And here, instead of using the Roberts construction, we have to use the Cayley construction. And part of the reason for this is because remember that a slider is equivalent to an infinitely long link. And with an infinitely long link, how do you draw a parallel line to that? I mean, it becomes an infinitely long parallel line, and you really can't do the construction. So you have to go to the Cayley construction, where you take this mechanism and you stretch it out. And so now I've got the stretched out being this ground pivot OA to this point should be labeled A to B, and I've stretched all that out on the horizontal axis, so I've stretched it out along the axis of slide. And then in doing so, I can take the coupler, and this was the initial coupler, AMB, and I've used the similar triangle effect of saying now I can make a similar triangle where I go B to OA, and that defines point C1 over here. And then the fact that I've got C1 and I know the position of the precision point, that then defines this coupler over here. And just like we did previously with the Cayley construction, I then pull this back to its initial, I bring this ground pivot OA back to its initial location. I take it from its stretched out condition, bring it back, and in doing so I move that C1 position, and it also pulls along with it the axis of slide that used to be right along this axis here. So it's basically a way of carrying that. And if you need to, I realize that what I've given you here is probably not enough detail to do this on your own. So if you're going to try to create one of these, I'd recommend heading back to the textbook. The original Hartenberg text has a great explanation of how to do this. So again, this is really more for your knowledge that if you're dealing with a crank slider, you have to treat it a little bit uniquely, but it does have 1 cognate. And then this would be the cognate, the crank slider cognate down here. And so this point M right here traverses the exact same coupler curve as the initial crank slider did. So one way to handle that. Okay, so with that, I just wanted to, that really ends what I wanted to cover. I do want to mention that there are a few programs out there that will construct cognates for you. The program 4-bar that's developed by Bob Norton and is sold with his textbook does create cognates of any mechanism for you. And what really becomes interesting there is if you use it to look at cognates of either straight line linkage mechanisms or other kind of specialty mechanisms that you might run into. but a little bit challenging to otherwise construct these. And so what I'd recommend doing is actually doing this in some sort of a CAD package. So you can certainly do it through the construction that we've done here, but I think it's a lot easier to CAD this up and force the similar triangles through CAD and be able to use that as your tool. And if you wanted to, you can almost kind of code that into CAD to force these cognate constructions if you're trying to do synthesis of a parallel motion 6-bar and you're going to synthesize lots and lots of path generators. I'd recommend coding this up in some form so you can create these cognates very quickly. Otherwise it can become very, very time consuming. All right, so that was the material that I wanted to cover today on cognates. Are there any questions about how you construct these, how you use them, other details?